Numericals related to atoms. Here you have question number 1. Calculate the shortest wavelength in the Balmer series of hydrogen atom. In which region, infrared, visible, ultraviolet, of hydrogen atom spectrum does this wavelength lie? Rydberg constant also is given. So we know that 1 upon wavelength is equal to z square Rydberg constant into 1 upon, and for Balmer series this quantity is 2 square. So 1 upon 2 square minus 1 upon n square. Here you have to find n. You have for calculating the shortest wavelength. Now this wavelength is shortest, then whole value will be largest. And for this largest value, this should be largest. And this right hand side is largest only when here what you are subtracting is smallest. And for that n should be infinity, so that this value becomes equal to 0. So on taking n is equal to infinity, you will have the shortest wavelength. Therefore 1 upon lambda is equal to, for hydrogen atom, z is equal to 1. So 1 into Rydberg constant, it is also given, value is given, into 1 upon 4 minus 1 upon infinity. This becomes equal to 0. Therefore lambda, 1 upon lambda is equal to r upon 4. And therefore lambda is equal to Rydberg constant. Lambda is equal to your 4 divided by Rydberg constant. This is 4 divided by 1.1 into 10 to the power 7 per meter. Here the value is given. So per meter, meter goes in numerator. So wavelength comes equal to, I have already calculated this for you, 3.637 into 10 to the power minus 7 meter. And this is equal to 363.7 nanometer. So this is your answer of first question. Question number 2. Using Rydberg formula, the same formula, calculate the longest wavelength. This time you have to calculate longest, belonging to Lehman series and Balmer series. You have now two separate series. So you will have to do two different equations, separate equations. In which region of hydrogen spectrum do these transitions lie? So let me first of all use formula for Lehman series. 1 upon wavelength is equal to Rydberg constant into 1 upon, and for Lehman series here you have 1 square and then minus 1 by n square. We have to calculate longest wavelength. When wavelength is longest, the whole value is smallest. And for smallest, this value should be largest. And for largest, the denominator should be smallest. This is how you will be thinking while doing. So n should be smallest. N be smallest. So what is the smallest value? When here in this term you have 1. So the smallest value n will be equal to 2. So we can find wavelength. 1 upon lambda is equal to, value of r also is given, 1 minus 1 upon 2. So therefore 1 upon lambda is equal to r into 2 square. Okay, here one term is missing, 2 square. So 1 minus 1 by 4, it is 4 minus 1 by 4. And therefore lambda can be obtained as 4 divided by 3r. This is equal to 4 divided by 3 into 1.1 into 10 to the power. Here you have value 7 per meter. Meter goes in numerator. Here you have numerator. So therefore lambda, for which lambda? Largest lambda. So lambda largest, I have already calculated this value for Lemon series, and this is your 1.21 into 10 to the power minus 7 meter, and this is 121 nanometer. So this is your first answer. Similarly, you can find for second series also, for Balmer series also. And you have to calculate longest wavelength. So let us start doing. Now, since 1 upon lambda is equal to r into, for Balmer series, this is your 2 square minus 1 upon n square. And for lambda to be largest, which is in denominator, you can see, this will be largest, only whole the value will be smallest. And if it is smallest, this value should be smallest. For getting this smallest, this subtraction term should be largest, and it will be largest if the denominator is smallest. So n should be anything 3, 4, 5, and the smallest value is 3 only. Here n is equal to 3 only. So this is how you will proceed. This is how you will think how to what should be the value of n. So therefore 1 upon lambda is equal to, Rydberg constant is already given, r into 1 upon 4 minus 1 upon 9. This is equal to 36, 9 minus 4, and therefore lambda is equal to 36 divided by 5r, and this is equal to 36 divided by 5 into 1.1 into 10 to the power 7 per meter, and meter goes in numerator. So therefore wavelength, this is your largest wavelength in Balmer series. This comes equal to, I have already calculated this value. This is your 6.54 5 into 10 to the power minus 7 meter. And you can write this value in nanometer also. 654.5 nanometer. So this is your answer of question number 2. So let us come on question number 3. Which state of triply ionized beryllium has the same orbital radius should be same as that of the ground state of hydrogen atom? So you know what is value of radius as per Bohr's atomic model? Radius r is given by epsilon naught n square h square upon z e square pi m. So here remember one thing, when you take two different metals, beryllium and hydrogen, they will have different atomic number z, but the rest of the things, epsilon naught, h, e, charge on electron, pi and m, mass on electron, all these are constant. So you have two different things that may vary. So r can be written as proportional to, here n can vary, n square by z. So comparing the r, because in question same orbital radius, the two has same orbital radius, for therefore radius for hydrogen atom for the ground state of hydrogen. Okay, ground state. It is your ground state. So I am writing here for ground state and giving a constant. Suppose the constant is K. Instead of giving proportionality sign in this equation, I have written here one constant. So for ground state in hydrogen atom, this is your 1 square upon, and the atomic number of hydrogen atom is also 1. And as per question, according question, radius for beryllium atom also is same. R hydrogen is same as R beryllium, and it is equal to R say. So R will be equal to this constant is same, and this n, you have to find n. So n square upon what is atomic number of beryllium, and this is your 4. So divided by 4. Now divide the two equations 1 and 2 and you will obtain the answer. R is cancelled, K is cancelled, and therefore n square upon 4 is equal to 1, and therefore n is equal to 2. So for triply ionized beryllium atom, you have the radius same for second cell as the radius of ground state of hydrogen atom. So here it is complete. Now question number 4. Using Bohr's postulate, derive the expression for the orbital period. You have to find out time period of an electron moving in ns orbit. So you know that time period t is equal to, just by the formula of velocity is equal to displacement per unit time. So time will be equal to displacement per unit velocity. And what is displacement? 2 pi r. This r is radius upon velocity. So here we will be putting the value of radius and velocity to find relationship between time and this number of cells, principal quantum number. Here we have to produce n on the right hand side, and then we have to find a relationship between t and n. Now, as we know that from Bohr's second postulate, mvr is equal to nh upon 2 pi. So from here we will be putting the value of v in equation 1. Now in 1 from 2, time period will be equal to 2 pi r divided by value of v, and this is your, from here you can find value, nh divided by 2 pi mr. So this is your time period is 2 pi r by v. Okay, v is your nh into this term will go in numerator 2 pi mr. Time period comes equal to 4 pi square m r square upon nh. Now still we have to convert this r into terms of n. So we know that from Bohr's model, we know that r is equal to epsilon naught. Here let me see the values. Epsilon naught n square h square divided by z e square pi m. So on putting value of r in this equation I think it is third equation. So now on putting value of R from here in 3, we find the expression for time period in terms of number of cells, principal quantum number n. So this is your 4 pi square m and r square. What is r square? Just square this quantity. So it will be equal to epsilon naught square n power 4 h power 4 divided by z square e power 4 pi square m square. So I have written 4 pi square mr square. This quantity is written and divided by nh. So divide this quantity by nh. Here one term in this equation will be cancelled. So do remember this quantity. This quantity is a very large quantity. Now there is one trick. You can find that all the rest quantities, mass, epsilon naught, h, all these are constant. Z also is a constant. Charge on electron is constant. Everything is constant. You can cancel some constant too. Like here, m is cancelled. So many other terms can be cancelled. Okay. So you can write that T is proportional to n cube divided by z square. This is a very important result. Do remember. Rest of the quantities are constant. So you should remember this result. Time period of an electron revolving in any cell in any stationary orbit is proportional to cube of that cell principal quantum number divided by square of atomic number. Number 5. A photon emitted during the de-excitation from the first excited level to the ground state. Here you have second cell. This is called first excited level. An electron makes a transition from second cell, that is your first excited state, to its ground state. Here energy of ground state is lower. So it will emit one photon of some energy. And that photon is used to irradiate a photocathode of a photocell. Here you have a photocell. So here in this question you have combined concepts of dual nature of light and atoms. So when a photon is emitted, it is made to fall on a cathode. And when a photon falls on a cathode, then it emits electron. Calculate the work function of the cathode used. So you have to find work function. Now, in which the stopping potential, what is stopping potential? It will stop the most energetic electron. Energy of stopping potential must be equal to kinetic energy max. So from here you can find kinetic energy max. Kinetic energy max is equal to energy of stopping potential and this is equal to, energy is equal to EV. V is given 5 volt. So this is 5 volt into E. So this is your 5 electron volt. In electron volt, kinetic energy max is your 5 electron volt. Now, so it is de-excited from first excited state to ground state. So what will be energy of that photon? We know that energy of ground state is equal to minus 13.1 13.6 divided by 1 square electron volt, and energy of first excited state, that is your second cell, is equal to minus 13.6 divided by 2 square electron volt. So what is energy difference? We will reduce smaller energy from the larger energy. So you have minus 13.6 by 4 minus of minus 13.6. It is equal to E2 minus E1. So therefore, energy emitted in the form of photon, E2 minus E1 is equal to energy is equal to h nu, energy of photon, and this is equal to, just let me make calculations, minus 4 3s are 12, 113, 4 4s are 16. So it is your minus 3.4 minus minus plus 13.6. So therefore energy of photon is equal to 10.2 electron volt. This energy will be in electron volt. This much energy is given here, this much energy, and a part of it will be utilized in work function, in taking electron out of the metal plate. So this energy, this is the main energy. This is your main energy. Energy of photon is equal to work function, energy for work function plus kinetic energy max. And therefore 10.2 electron volt is equal to work function plus kinetic energy I have obtained. This is your 5 electron volt. Kinetic energy max is equal to 5 electron volt. Therefore, work function of the metal plate is equal to 10.2 minus 5 electron volt, and this is 5.2 electron volt. Answer.